In this video, I will explain quantum mechanics in 5 minutes. Let's look at this equation first. H psi equals IH bar times delta psi over delta t. H is the energy operator. Psi is the wave function of the system of interest. I is the square root of -1. H bar is the Planck constant divided by 2 pi. H bar is roughly 10 to the power of -34 joules second. Over here, this is simply the first derivative of psi with respect to time. This is a partial derivative because psi also depends on the coordinates of the particles in the system. By solving this equation, we can predict the behavior of the system. The system can be just one electron or the entire universe that consists of 10 to the power of 80 particles. Again, H is the energy operator. Therefore, H is the sum of the kinetic energy operator and potential energy operator. The potential energy operator looks easier. It depends on the positions of all the particles in the system. It also depends on time. So you see this time here. What about the kinetic energy operator? If we have more than one particle in the system, we need to sum up the kinetic energies of all particles. That's why you see this sum sign here. If we're talking about the universe, then we have this I from 1 to 10 to the power of 80, if there are 10 to the power of 80 particles in the universe. And this is the Laplace operator, or Laplacian, the sum of the second derivative with respect to x, y, and z of the ith particle. Over here, negative h bar squared over 2m, and this m is the mass of the ith particle. So I made a mistake here. I was assuming all particles have the same mass, but they don't have to. So I'm putting this m sub I here. And it's better to move this negative h bar squared over 2mi inside the sum. Alright, so again, this is the kinetic energy of all particles. And this is the potential energy that depends on the positions of all particles and time. So now, given the wave function of any system at time t1 and its Hamiltonian, so over here you have the Hamiltonian here, we can predict its wave function at any other time by solving this Schrödinger equation. However, the math can be really hard. So one way to do this is we just write out this psi at t2 equals psi at t1 plus the integral of h psi over IH bar times dt. Alright. Why this? It's very simple. We just have both sides divided by IH bar and multiply by delta t, and then we integrate both sides, we get this equation. Alright. So again, this h does depend on time. This psi also depends on time. The time-independent Schrödinger equation is a bit easier. So this psi does not depend on time. This h does not depend on time either. And then we just need to solve this equation to get the physical and chemical properties, any properties for any system. How do we do this? There are 5 steps. First, write out the energy operator. Again, the energy operator takes this format. You have the kinetic energies of all particles plus the potential energy, which depends on the positions of all particles. There's only one change in the time-independent Schrödinger equation. V does not depend on time. So we need to delete this time in the time-independent Schrodinger equation. All right, so write out the energy operator, and then find all eigenfunctions psi. You can say psi sub 0, psi sub 1, psi sub 2 of this Hamiltonian. This is the hard part. Very often we have to come up with approximate solutions, except for the systems that contain only one or two particles. For example, the hydrogen atom contains only two particles, one nucleus and one electron. Helium plus, lithium 2 plus, beryllium 3 plus, and boron 4 plus all contain only two particles, one nucleus and one electron. Therefore, we can solve the Schrodinger equation for those ions exactly. Assume that we have solved the Schrodinger equation. That means we have found all the eigenfunctions for this Hamiltonian, and then this psi squared. To be more accurate, the squared modulus of psi is the so-called probability density. Psi squared times d tau is the probability of finding that system within the d tau volume element. Again, if we have psi, we can easily take the squared modulus of psi. And this can be obtained by multiplying psi star and psi. Psi star is the complex conjugate of psi, and we can simply replace every single I, the square root of -1 in psi, with -I to get its complex conjugate. And then we multiply psi star and psi to get the squared modulus of psi. Or another way to do it, this squared modulus of psi is the real part of psi squared plus the imaginary part squared of psi. Step 4. We can use quantum mechanical postulate 3 to obtain the exact value of a physical quantity O by applying this corresponding operator to the wave function psi. How do we do this? Very simple. If you need to know the momentum of this system, just apply the momentum operator to psi. The momentum operator is -IH bar delta over delta x for the momentum in the x direction. And then if you're lucky, the psi is an eigenfunction of this operator, you will be able to get the exact value of the physical quantity of interest, O. This O is a constant. This O is the exact value of the physical quantity. But you have to be really, really lucky to have this psi be the eigenfunction of the physical quantity operator. Very often, step 4 does not work, and then we can still obtain the so-called expectation value of this physical quantity by evaluating two integrals. So on the bottom, it's just the integral of the squared modulus of psi. On top, it's the integral of a product of psi star, the complex conjugate of psi, and O psi. So this part is this O operator being applied to psi. So you need to evaluate this part first, and then do the multiplication, and then integrate this product with respect to d tau. And d tau is the volume element. And this integral is from -infinity to positive infinity. This suggests that we are integrating the psi star times O psi over the entire space. And then we'll be able to get the expectation value of this physical quantity O.